In this example, we're going to do what's called a banked curve question. And what that means is a car is going to be going around a corner. So if you can picture it from the viewing from above, if a car goes around a corner, because of its inertia, it tends to slide outwards unless there's friction to kind of hold it in, some static friction. That is what normally prevents the sliding. In this case, if it's an icy corner, what that means, that's kind of code in physics for there's no friction. If there's no friction, then a car can't go around a corner unless this corner is banked. Okay, so we're going to do what's called the banked curve, and I don't know if you can tell from my hand, but I'm going to tilt it this way. If I view it from behind, what that is going to mean, let's see if I can give myself a little more room. If I bank the curve, let's see if I can draw this. I'm going to try to draw it a little big so you can picture it. If I'm looking at the car from behind, the road surface itself is going to be banked. So right here, let's imagine that there's a car. I'm looking at the rear license plate. The car is going into the page this way. So as the car goes in that way, I'm standing behind it and I can see the car. I can see that there's a force of gravity going down this way and a normal force going up this way. Okay, so here's the normal force, here's the force of gravity. The road is banked at this angle, so this line here represents horizontal. The actual road surface is tilted, and as the car drives into the page, so this is like a rear view, let's say rear view. This is a rear view of the car going into the page. I'm standing behind it looking at it. Here's what I see as the car goes into the page. If there's the normal force, remember normal force is perpendicular to the surface that I'm on. Gravity is straight down. You could say gravity is perpendicular to horizontal. So this line represents horizontal. What I'm going to imagine then is as the car is going in this way, it's going to go in like this and come back out, kind of go in this way and back out on the other side. I don't know if my hand, if you haven't watched the lesson video, in the lesson that I posted, there's a video of a roller coaster, and you can kind of see it go around a corner, and the actual corner itself is banked. What that means is the center of the circle is right here. Okay, so if the car is here, it's going in on this side, it's going to come back out on the other side. The center of the circle is here. That means acceleration is towards the center of the circle. Okay, so I'm going to draw over here and say, my coordinate system, since acceleration is going this way, let's say A, it's actually a centripetal acceleration, so that's kind of small, but AC. What that means is I do not want to tilt my coordinate system. If you can remember back to when we talked about tilting our coordinate system or not tilting our coordinate system, if acceleration is going this way, AC, I want it to lie on one of the axes of my coordinate system, in this case, the x-axis. Okay, so I'm not going to tilt my coordinate system. I know your common kind of intuition tells you we should tilt it because it's going to slide down. It's not. It's actually going to, if it's going around in a circle, it's going to tend to move outwards because of the road. It's going to tend to try to slide upwards. Okay, so I'm not going to tilt my coordinate system because acceleration is in this way towards the center of the circle. That means I'm going to have to break up this normal force. Normal force I'm going to have to break up into Fny, and right here, if I can just squeeze in here, Fnx. Okay, so there's Fnx, there's Fny. This angle right here is that angle right there between Fny and Fnx. So I'm going to start off and I'm going to look in the vertical direction and the horizontal direction, kind of at the same time. So let's start vertical over here. If I'm looking in the vertical direction, remember we said here, or maybe right here, we said the centripetal acceleration is towards the center of the circle. There is no acceleration in the y direction. Okay, so we could start off and say sum of forces in the y direction is equal to 0. If that's true, what that means is this upwards force here has to equal this downwards force right there. Okay, so we know Fny is equal to Fg. The y component of the normal force is Fn times the cosine of theta, because this is the adjacent side. So this thing here is Fn cos theta equals mg. I can rearrange and solve this thing for Fn. I just know from experience that I'm going to have to do that. And you'll see why in one sec. Okay, so I'm going to do that. I'll say here, this is kind of like an equation 1. I'm going to need this equation. I'm going to need to do something with it. I'm also going to look horizontally because I'm kind of stuck over here, right? I don't know the mass. I know the radius. I know the speed. I'm looking for angle. I don't know the mass. I can't solve this thing. I don't know the angle. So let's look horizontal. If I look in the horizontal direction, there is an acceleration. This is circular motion. Again, we're viewing from behind, but as the car goes in, it's going to come back out on the other side. So this is a circular motion example. The only force that's pointing kind of in or out in what I would call the x direction is this Fnx up here. Okay, so Fnx is equal to mv squared over r. Just like we did over here, Fny was Fn cos theta. This thing is going to be Fn sine theta equals mv squared over r. There's equation 2. Okay, so the reason I solved for Fn here is because I know I'm going to need to sub this Fn in right over here. Okay, so what I'm doing is subbing 1 into 2. Okay, so let's actually come up here and do that. I'll say it again right here. Sub 1 in 2. I'm going to take this whole thing, this whole big bracket, it's going to go right in there. Okay, so let's put the brackets. We don't really need these brackets, but let's put them just so you can see what I'm subbing in. This thing here over cos theta. That's Fn. I still have a sine theta out here. And that's equal to mv squared over r. We don't have to do this, but we can say, if you can remember from your math class, sine theta divided by cos theta is tan theta. So we could say this is mg tan theta equals mv squared over r. We've got m on both sides. We can divide both sides by m. We're going to cancel that guy out. What we're left then with is g tan theta equals v squared over r. And we can find a few different things with this. What we're asked to find is the angle, but depending on what you're given in the question, we know here this is radius, this is v, so I'm going to sub into this. I'm going to bring g over and solve for theta. But in other questions, I might be asked for the speed or the radius. As long as I know sort of 2 out of the 3 of those things, there's a common kind of statement that I can solve from. I'm going to go ahead and say tan theta is equal to, this g is going to come down, so v squared over gr. What I want to solve for now is theta. So let's move over just a little. Tan theta is equal to v squared 15. Again, don't forget to square. G 9.8. Radius 48. And we'll work this thing out. Theta is 25.6. Let's say for sig digs, theta approximately 26 degrees. And there's our answer.